And if you need to learn more about diagonalization of a matrix, you can always contact me to watch this entire video. We start with a few properties of eigenvalues. If A is a square matrix, A and A transpose have the same eigenvalues. A dash, as you know, stands for transpose of A. The eigenvalues of a triangular matrix are the diagonal elements. The eigenvalues of a diagonal matrix are also the diagonal elements. The eigenvalues of an idempotent matrix are 0 and 1. The trace of a matrix is the sum of the elements of the principal diagonal, and the sum of the eigenvalues of a matrix is also the trace of the matrix. The product of the eigenvalues of a matrix will be the determinant of the matrix. If lambda is the eigenvalue of A, then 1 by lambda is the eigenvalue of A inverse. If A is an orthogonal matrix and lambda is its eigenvalue, then 1 by lambda is also its eigenvalue. And if lambda 1, lambda 2, lambda n are eigenvalues of A, then lambda 1 raised to m, lambda 2 raised to m, up to lambda n raised to m are eigenvalues of A raised to m. Now, Cayley Hamilton Theorem says that every square matrix satisfies its characteristic equation. So, based on this question, we will just do a small question. Find the characteristic equation of A equal to 1, 4, 2, 3, and hence find A inverse. We know that there are multiple methods to find the A inverse, but here we will find the characteristic equation first. So first we will write determinant A minus lambda I equal to 0. That's how we find the characteristic equation of A. So I get determinant of 1 minus lambda 4, 2, 3 minus lambda equal to 0. So simplifying this, we get 1 minus lambda into 3 minus lambda minus 8 equal to 0, which will give you 3 minus 4 lambda plus lambda squared minus 8 equal to 0. On simplifying, you get lambda squared minus 4 lambda minus 5 equal to 0. And so by Cayley Hamilton theorem, every matrix satisfies its characteristic equation. So I have A squared minus 4A minus 5 equal to 0. So this is actually the characteristic equation of A. To find the characteristic equation of A, we do determinant A minus lambda I equal to 0. So now this is the characteristic equation of A, and now we will find A inverse. So pre-multiply both sides by A inverse. So I get A inverse into A squared minus 4A. So this I can write as 5I minus 5I equal to 0. So multiplying, I get A minus 4I minus 5A inverse equal to 0. Simplifying, you get A inverse equal to 1 by 5 into A minus 4I. And if I were to substitute, you get 1 by 5 times 1, 4, 2, 3 minus 4, 0, 0, 4, and this would reduce to 1 by 5 times minus 3, 4, 2, minus 1. Coming to the next question, find the characteristic equation of this matrix, and hence find the matrix represented by this equation. So first of all, we will calculate determinant of A minus lambda I equal to 0. So I can write it as 2 minus lambda 1, 1, 0, 1 minus lambda 0, 1, 1, 2 minus lambda equal to 0. And simplifying it, you get 2 minus lambda into 1 minus lambda into 2 minus lambda minus 0. Then you get minus 1 into 0 plus 1 into 0 minus of 1 minus lambda equal to 0. So simplifying, you get 1 minus lambda into 2 minus lambda the whole squared minus 1 equal to 0. Or 1 minus lambda, if I expand, I get 4 minus 4 lambda plus lambda squared minus 1 equal to 0. And simplifying further, you get 1 minus lambda into lambda squared minus 4 lambda plus 3 equal to 0. And if we were to multiply, we get lambda squared minus 4 lambda plus 3 minus lambda cubed plus 4 lambda squared minus 3 lambda equal to 0, which will give you minus lambda cubed plus 5 lambda squared minus 7 lambda plus 3 equal to 0. You can multiply by minus 1, so I get lambda cubed minus 5 lambda squared plus 7 lambda minus 3 equal to 0. And every square matrix satisfies its characteristic equation. So by Cayley Hamilton theorem, we can say that a cubed minus 5a squared plus 7a minus 3i equal to 0. Now coming to what the matrix which we are given, it looks complicated, but actually it's not. A raised to 8 minus 5 a raised to 7 plus 7 a raised to 6 minus 3 a raised to 5 plus a raised to 4 minus 5a cubed plus 8a squared minus 2a plus I. You can take out the a raised to 5 and write it as a cubed minus 5a squared plus 7a minus 3i. Here I can just take out the a and I get a cubed minus 5a squared plus 7a minus 3i. And we know that from this 1, these two terms will give you a 0. So you get it as, and then you have the remaining terms plus a squared plus a plus I. So I have taken these terms, and then here I have taken a times a cube minus 5a squared. So minus 5a squared plus 7a, so you have 8a squared. So I can write it as a squared plus a plus I. You can actually simplify it. A raised to 4 minus 5a cubed plus 7a squared plus a squared is 8a squared. Then you have plus 7a plus a minus 3a plus a will give you minus 2a, and then you have minus 3i. This is plus 7a minus 3, there is no a here, 7a minus 3, and minus 3a plus a will give you 2a, and then you have a plus I here. And these terms are 0, so you get it as a squared plus a plus I. So this complicated equation reduces to a squared plus a plus I. You can actually simplify and see for yourself. Now if you have to calculate a squared, you get it as 544,010,445 plus a. A is 211,010,112 plus I. I is 100,010,001, and when you simplify, this reduces to 855,030,558. So this is what this matrix on the LHS reduces to. So we have come to some basic properties of eigenvalues. We have gone through that, and we have learned how to calculate the characteristic equation of A and some simple problems based on these. Now the rest of the video consists of more properties and diagonalization of a matrix. Students who need to watch or learn this entire video can contact me. Thank you.